Hello everybody, my name is Hannah and welcome to today's General Maths July lecture. So this lecture is hosted by ATAR Notes, which has been around since 2007, and we offer a whole bunch of free resources to help our high school students thrive in their studies. And today's lecture is just one of those. Along with the lectures that we run, we also have got some free study notes you can download. There's discussion forums, videos, newsletters, there's an online ATAR calculator, there's articles and heaps more. So if you are interested in finding some more free resources, please head to atarnotes.com and check out the range that we have. And if you're also interested in some further and maybe more detailed paid resources, we have a range available as well. We're starting to bring out some flashcards, which are a really cool option. We also have our course notes. We have question books out for some of our math subjects. We also have text guides, and there's even an AI answer bot available with ATAR Notes Plus. So if you are looking for those further, more specific resources to really help you with your study, make sure you head to atarnotes.com again and check out those resources. So, like I said, today's lecture is for General Maths, and we'll be focusing on Unit 4, going through some of the content, doing some practice questions, all of those kinds of things. A little bit more information about me, just to introduce myself. Like I said, my name is Hannah. I graduated high school in Queensland in 2021, so I myself went through the ATAR system, so I'm quite familiar with the content, the structure, the assessments and all of that. And I studied biology, psychology, English, general maths, drama and outdoor sport and rec. So I really enjoyed the variety of subjects that I had. And I'm also currently studying primary and secondary education, majoring in biology. And again, if anyone has any questions throughout, please feel free to chuck them in the live chat box, whether that's related to like the content, the questions, if you'd like us to clarify something, or questions about uni, anything at all, please feel free to ask those questions and we'll do our best to answer them and get to them as soon as we can. So a bit of an overview of what today's actually going to look like. Because it is already July, we'll be focusing on Unit 4. We'll kind of get through as much of the content as we can. So we'll hopefully be able to make it through loans and investments, graphs and networks, and also cover some of decision maths, cover some tips and tricks to help you with like preparation for your external and all of those kind of things. And again, please feel free to make the most of the live chat box. And like I said, we are just doing like some overview. We'll only be exploring some types of questions and some of the content that's a part of the syllabus. So make sure you do keep referring back to the syllabus to make sure that you are that your revision and your study is covering all of the content descriptors in the syllabus to make sure that you are getting the whole picture of what you need to know. Because again, today is more of an overview and we'll focus in on different topics. And again, if you would like to download the slides or rewatch the video, you can do that from this page here. Feel free to pause if you'd like to take a break. And I'm also going to try and make lots of active connections between content to try and consolidate your understanding and help in that kind of area. So try to do this as well, answering any questions that I might pose or linking back to prior knowledge, because this does help improve active recall. So I'd love it for everyone to be as actively engaged as possible, and make sure you stay tuned because I've got practice questions spread all throughout the lecture today. So those will hopefully be really helpful for exam preparation as well. All right, let's get into it. So topic 1 is loans and investments. So we're talking about money. When we're talking about loans and investments, we're really just talking about money. So my first little connection that I have to prior knowledge to make that link for you today is geometric sequences. Hopefully it hasn't fallen out of your brain too much and you remember studying geometric sequences in Unit 3, which would have been probably a few months ago. So geometric sequences is where we take a starting point and then we multiply it by a constant factor, which when we're talking about geometric sequences, that's r, and then we take our new term and do the same. So we take our starting point, which for example could be the number 3, and then we multiply it by a constant factor, which could be the number 2, for example. So we take our starting point, 3, multiply it by 2 and get 6, and then we times that by 2 again and get 12, times that by 2 again and get 24, and it can go on and on and on and on because it's a sequence. So we're just applying the same rule repeatedly. And the good news that I have for you today is that compound interest is essentially a special application of geometric sequences. So we're actually doing quite a similar thing if you think about it conceptually when we're doing a compound interest, because we're taking a starting point, which would be the amount of money in the investment or the loan, and then we're multiplying it by a constant factor, which is the amount of interest being paid or owed, depending on whether it's a loan or an investment. And then just like in our geometric sequences, our number grows exponentially as it's multiplied by the constant factor. The same happens in our loans and investments because the sum grows over time. So for example, you think about superannuation. The reason money is put aside into superannuation accounts and set aside for retirement is that, or the reason that people choose particular funds to trust their money with, is that hopefully compound interest will be being applied to that money so that the sum in that account can grow, as well as the contributions being made by a person's employer. Same might occur in like a long-term or like a savings account, or also if somebody has a mortgage or a house loan, there's always going to be this compound interest at play. So we're going to be talking about that a little bit more today to hopefully either revise it or further develop your understanding of that a little bit more. So just like with sequences and with simple interest and with compound interest, we can calculate it using a recursive definition. So the idea of recursive is when we take the starting point and then we apply the same rule to get our second term, and then we apply the same rule to get our third term, and then we go on and on in that fashion. And the rule that we use to do that in the case of compound interest is n plus 1 is equal to r multiplied by an, where a0 is the initial quantity. So if, for example, someone invested $2,000 into a bank account, then $2,000 would be a0 because that's the initial starting point of the money. An is the amount owed after n periods, or the amount made if it's an investment. Because again, this can apply to both a loan or an investment, because in an investment, the amount of money that you personally have is growing, but in a loan, the amount of money that you owe is increasing because interest is being charged on the money that you've borrowed. So an, the amount owed after n periods, and then r is our rate of interest. It's like the factor by which the amount of money is growing by each period, and that we can calculate that by saying r equals 1 plus I over m. And I want you to take note of this carefully, because some textbooks might define this as like x over m or x over I or k over t. There's all these different variables that different like textbooks and courses and structures and programs use to define this. So the important thing isn't to memorize the letters. The important thing is to actually know what the letters represent, so that if you are given this formula or if you memorize this formula, you actually know how to use it. You're not just writing down letters that you actually don't know what they represent. So a better way to think of this rather than I over m would be r equals 1 plus the decimal interest rate per annum divided by the number of compounds per year. So when we're talking about the decimal interest rate per annum is referring to yearly. And when we're talking about decimal, that means like in decimal form. So if the interest rate on a loan or investment was 5% per annum, then we'd say 0.05 divided by the number of compounds per year. And if it's compounding annually, then there's 1 compound per year. If it's compounding monthly, then we have 12 compounds per year. If it's compounding weekly, we have 52 compounds per year. So those are kind of the different ways that we define the variables. So let's do an example to hopefully make that a bit clearer. So let's say we invested $1,000, which should be our starting value, at 5% per annum, compounding annually for 2 years. So we'll start filling in and labeling our variables to work out what we know and how we can get our answer. So A0, our starting point, like I said, is $1,000. And AN is the quantity after N periods, which in this case is our unknown. So AN is like the variable that we're trying to find. And R, like we said, it's the decimal interest rate divided by the number of compounds per year. And here, our decimal interest rate is 5% per annum. So we've taken that, turned it into a decimal. So we've got 0.05, and we have 1 compound per year because it's compounding annually. So our M is 1. And we want to make sure that we're adding 1 as well. So our R, which is the rate by which our loan is growing, is 1.05. And next, that's all we've been able to define. So now we start by just like solving the formula and working out what the value is after 2 years. So to do that, the first thing we'd say is let n equal 0. So what we'd do, we'd take this formula here, say let n equal 0. So then we'd have a 0 plus 1. So that would give us a1 is equal to r multiplied by a0, our starting point. So that's what we've done here, a1, so the amount after 1 period, the amount after 1 year, in this case, is equal to 1.05, the factor by which it's growing, multiplied by the amount that we had to start with, which is, in this case, $1,000. And that gives us $1,050. So here we can see that the quantity after 1 year is $1,050. But we're being asked what's the quantity after 2 years. So then we've got to apply our recursive rule again. So we'd say let n equal 1. So now we're saying a2 is equal to r times a1, which makes sense because we're applying the rule to the following year. So we're saying, well, how much would there be after 2 years? And we can work that out because we know how much was there after 1 year. So we'd say the amount after 2 years is equal to the amount at the end of the 1 year, and then multiplied by the same factor because it's growing by that same amount. And that'll give us $1,102.50. And you'll notice that here we made $50, but here we actually made $52.50. So you'll see that we actually made a little bit more money the second time around, and it would be the same if we kept applying the rule. Each time we'd be making a little bit more money. And that's the whole idea of compound interest, because that's kind of the differentiating factor between simple interest. Simple interest could be modeled by arithmetic sequences, because simple interest is that scenario where we're adding the exact same amount every time. We're getting $50 interest every time. So it would form that linear pattern. But when we're talking about our compound interest, we're modeling that kind of in a very similar manner to geometric sequences. You can see that it's actually growing by a little bit more each time because we're applying our rate of growth to the previous new amount. So the amount of interest, or the amount of money that we're earning interest on, is growing. So the amount of interest we're earning is growing as well, because interest is based off like a percentage. So that's the really cool thing about compound interest. But what if we invested $1,000 at 6% per annum for 2 years? So the difference here in this scenario is in our last question, we were looking at what if we invested at 5% per annum. But here we're asking, but what if we invested at 6% per annum? So we'll do the same thing. We'll work out our formula. Our starting point is still $1,000. We still don't know AN. The goal is still to find out how much money we'll have after 2 years. But here R is a little bit different. Our decimal rate of interest is 0.06 instead of 0.05, because now we've got 6% per annum instead of 5% per annum. So the money that we have in that compound interest loan or investment is growing by 6% every year rather than 5%. So it's going to be growing more each year. And when we get our answer, that'll illustrate that. So again, we'll say let n equal 0. So the amount of money after 1 year will be equal to our starting value multiplied by the factor that it's growing at. And that'll give us $1,060. And you can already see that we're already $10 better off. And then we apply the same to find out how much after 2 years. We take our new value, $1,060, and we're multiplying it by 1.06. And you can see that now we've made we have a total of $1,123.60, which we can see is quite a bit more than when we were only calculating at 5% per annum. So you can see it's quite beneficial. If we had an investment, we would actually want a higher rate of interest because that would mean we would be earning more money. But the interesting thing is, if it's a loan, we would actually want the lower rate of interest because we don't want to be paying interest. We want to be paying as little interest as possible. But if it was an investment, then to choose the option that would work best for us, we would want to choose the higher rate of interest option. So that's an interesting thing to think about. Okay, so now we're going to have a look at another scenario. So what if we invested $1,000 at 6% per annum, but what if it compounded monthly? So before we had yearly compound, so our loan or investment only compounded once a year. Well, here we're talking about an investment. But now we're looking at a scenario where what if it actually compounded monthly? So again, we'll take the same formula. We have the same starting point. We have the same end goal. We want to find out how much money are we going to have in our investment after 2 whole years. But here, again, is where we have another slight change in how we find R. So R is no longer telling us how much our money grows by every year. It's telling us by what factor does our money grow by every month. Because now we're looking at monthly compounds. So I is the same as in our last question. It's our decimal rate of interest, 0.06, because we've got 6% per annum. But the interesting difference here is that now instead of 1, we have 12. Because M, if we remember, was referring to the number of compounds per year. And if it's compounding monthly, then we're going to have 12 compounds per year. So R, the rate by which our investment is growing every month, is 1.005, which is a smaller number. Oh, sorry, that's my mistake. That should be 1.006 because it's divided by 12. Yes, sorry, 1.005. My bad, that is correct. So it's growing by 1.005 every month, which is a smaller number than with 1.06, which is what we were looking at before. But now we're kind of wondering, well, before when it was 1.06, that was only compounding once a year. But this 1.005 is going to compound 12 times a year. So I wonder which one's going to give us like the better outcome. And let's have a look at it. So when we're looking at monthly compounds, recursion is going to take a little bit longer because we need to look at the compound for every single month. So let n equal 0. So here we have A1, and because we're looking we're not looking at yearly time periods anymore, we're looking at monthly time periods. Here we're saying the amount after 1 month will equal to $1,000 multiplied by our growth factor, 1.005. So we're going to have $1,005 after 1 month. And then if we say let n equal 2, then it'll be A, 1 plus 1. So A2, the amount after 2 months, will be equal to $1,005 multiplied by 1.005, and that will give us $1,010 and 0.025 cents. So you can see that our amount is starting to grow bit by bit. And then the amount after 3 months will be about $1,015. The amount after 12 months, so the amount after 1 year, will be $1,061 and about 68 cents. Then if we keep going, the amount after 24 months, which we know is 2 years, will be $1,127.16. Instead of when we did annual compounds, it was only $1,123.60. So we've made about $4 extra over the 2 years. And that's definitely not a whole lot of money, but it does illustrate the fact that more regular compounds mean we actually earn more money overall because it's compounding more frequently. So, and you can definitely think about or imagine like how much of an impact that would make if we had a time period of longer than 2 years, or if we had an amount over like more than $1,000. So for example, a home loan, for example, of like $500,000, whether it compounds monthly or annually, could make a really big difference to how much we owe at the end of the time period. So here are a few of the takeaways from those examples that we looked at. So when we increase the interest rate, the amount will also increase, because when the interest rate goes up, more interest is being applied, so the amount is going to grow quicker. And also, when we increase the number of compounding periods, the amount will also increase. So if it compounds once per year, compared to if it compounds 12 times per year. Compounding more times per year, so for example, the 12 times per year, that means the amount will increase more. So like I said, it's like if we're increasing the number of times our money compounds, that's how it kind of equates to increasing the amount of money that we do get from that. And this is what I said before, and this is a very, very important thing to take note of, and something that's going to be really, really important in a lot of the questions that you get asked. So whether you want a higher or lower interest rate, or whether you want more or less compounds per year, depends entirely on whether it's a loan or an investment. Because in either scenario, we're going to want to make the choice and choose the option that works financially best for us. So if it's a loan, we are going to want a lower interest and less frequent compounding periods, so we're not paying as much in interest. But if it's an investment, we are going to want a higher rate of interest and more frequent compounding periods so that we're actually earning more money off our investment. So if you're asked a question about should somebody choose 5% interest or 7% interest, for example, the first thing you should be thinking of, well, is it a loan or is it an investment? Because that is entirely and 100% going to influence whether they choose the 5% or the 7%. So it depends on whether it's a loan or an investment, because we're always going to want the best option financially for yourself or the person in the question, depending on whether it's a loan or an investment. So compound interest using recursion is quite time consuming. So what if we wanted to do it without recursion? Thankfully, we have a formula for that, so we can do it. And this is a formula that many of you are probably familiar with. So AM equals P, open bracket, 1 plus I, close bracket, to the power of N. So what do these variables mean? So first, P is the principal, and that's the initial quantity. So if, for example, we had like $20,000 in a bank account, then that would be the principal. That's like our starting point. And then I is X divided by M, where X is the interest rate per annum, so again yearly, and then M is the number of compounds per year. And this is like what I highlighted before. I wanted to just quickly mention again that it's really important to notice, or to be very cautious about how we are actually defining our variables. Because again, it's not about what letters we use, because sometimes that changes from formula to formula, because here I has to be that value there, but I is actually equal to this, so we can't have I in the same position that it was last time. So it's really, really important not to trip up and make a mistake when you're defining your different variables and values. It's not important to memorize what I is, what X is, what M is, or if you do have consistent letters that you use for this in your own study or in the own rules that you use, then that's awesome. Keep running with that. But the most important thing, again, is to remember and define what it is we're actually doing. So here, we're saying that I is equal to the decimal interest rate per annum divided by the number of compounding periods, like how we defined R before. We're just talking about it a little bit differently. But when we defined R in a recursion, we said 1 plus the decimal interest rate per annum divided by the number of compounds per year. But here, we actually don't have a 1 plus, because that 1 is already built into the compound interest formula. So make sure you don't add another 1, or it'll end up being 2.0 something, and that would be quite a high rate of interest. So yes, make sure you take that into account. So yes, P, principal, our initial value, 1 plus the decimal rate of interest divided by the number of compound periods per year. So yeah, number of compounds per year, and then to the power of N, which is the total number of compounds. So say, for example, we had a loan or investment that was compounding monthly, so 12 times per year over a 3-year time period. That would mean N would be equal to 12 times 3, which is 36, because the total number of compounds in this loan or investment would be 36, because that means it's compounding 36 times, because it's compounding every single month for 3 years, which 36 months is how we get 36 compounds. So let's do a question to kind of illustrate a little bit further. So let's go back to our scenario where we had $1,000 as our initial value, and it was compounding monthly for 2 years, so 24 compounds total, at 6% per annum. Let's define our variables. So P, principal, initial starting value, was $1,000 that we had. And I, was defined as our decimal rate of interest per annum, which was 6%, so we get 0.06 because we take 6 and divide it by 100 to get our 0.06, and then we divide it by 12 because that's our number of compounds, so we can see that our I is 0.005, which is what we found. R was 1.005 in our previous question. And then, like I said, N is going to be 24 because it's compounding monthly over 2 years. And then we can substitute into our formula. So we've substituted in the value for P, the value for I, and the value for N. And then all we need to do is put that in our calculator and solve for it. And we can see that we actually got the same answer we got when we used recursion. This was just a much quicker process than having to apply the same rule 24 times over. Whereas here, we only had to fill in the one formula. So that is the beauty of the compound interest formula. So we're going to do a practice question now from one of the NEEP trial exams, which are really good resources if you're after some practice questions to do. So this one says, a person wishes to put $2,000 into a saving account and they want to receive $600 of interest. So we're being told different information this time, which is interesting. The interest rate we're told is 3.15% per annum, and we're told that we have monthly compounds. All really important information. So we're told to calculate the number of years and months it will take for the person to receive $600 of interest. So interesting, we've been given different variables this time. So we're still going to start with our same starting point. A equals P, 1 plus I to the power of N. But here, A is not our unknown. We actually know what they want A to be. They're going to put $2,000 in to begin with, and they want to receive $600 worth of interest. So their desired end goal amount for this investment is the initial amount plus how much they want to earn in interest. So the goal amount in this scenario is $2,600. We also know P, the principal, because we're told how much they're going to invest. So we know that the starting point is $2,000. And we can also calculate I. They've arranged their formula slightly differently here, but it's still the same effect as what we've been talking about. So what they've done is they've taken the interest rate per annum, which is 3.15%, and then think of it like they've divided it by 100, and they've also divided it by 12, which is the number of compounds per year. So they've done the exact same process. They've just set it out a little bit differently. So we've calculated I, and then that's what we know. So now we can substitute it into our formula. We know that A is $2,600. We know that P is 2,000. We know that in our brackets we'll have 1 plus the value for I. And then we'll also, that'll just leaves us with N as our unknown, which makes sense because the question is asking us to calculate the number of years and months it'll take for the person to receive $600 of interest. So the unknown is the time period. So that's the N. So that's what we're trying to find out. So what they've done to simplify this is they've divided each side by 2,000 so that we can isolate more of our variables. So we took 2,600 and divided it by 2,000. We divided this side by 2,000 as well, and that cancelled out. So we're left with 1 point, our I value to the power of N. And now to solve for N, we're actually going to use trial and error, which is a totally appropriate method to try and find the value of N, because otherwise we'd need to use like logarithms, and that gets really complicated, and we actually don't learn that in general maths. So that's not actually a way that we need to use to solve the problem. So to use trial and error, we choose different values for N. We're going to say let N equal this, and we'll see if that works for our equation. So for example, what if we let N equal 5? Well, if we put this number to the power of 5, it would equal 1.0131, and the number would go on, but that's way, way lower than 1.3. So, and we know that's nowhere near equals 2, so we know that that N value is going to be far too low. And then what if we said, well, let n equal 200? That'd give us 1.68, which is way too high. So we know it's going to be less than 200. What if we try n equals 100? That'd give us 1.2997, which is really, really close to 1.3. But that means we still haven't hit 1.3. So that means we're still not at the right point. What if we let n equal 101? Then that would give us 1.3031, and it would go over, and then ... And that is just over the required value. So we know that n equals 101 will meet the requirements of the equation that we're looking at. So that means when the money, our initial quantity, has compounded 101 times, that is how long it will take them to reach the desired amount. And because we're talking about monthly compounds here, n equaling 101 means that it will take 101 months for them to reach $2,600. And we can actually convert that into months and years. So therefore, it will take 8 years and 5 months to receive $2,600, and that will give them their desired goal of that $600 of interest. So that's how I would approach a question such as this one. So it's important to note that we don't just need to use the compound interest formula for loans or investments where the amount is unknown. Like with any other formula, we can actually rearrange it and solve for other variables. So that's one question example there. So in some questions, you might be asked to compare multiple interest rates, like we've already talked a little bit about. You might be asked, well, which one's the better value, this one or this one? And I've already mentioned that a higher or lower interest rate or more or less compounds per year would be, and we've talked about what you'd choose depending on whether it's a loan or an investment. But what if we have different interest rates per annum and different compounding periods? Then it's going to be really hard to compare them on equal footing. So for example, should I invest at 6.1% per annum compounding annually, or should I invest at 5.95% compounding weekly? Well, this first option looks better because it's got a higher interest rate, and I know that if there's a higher interest rate, that means I'll get more money back on my return. But I also know that more frequent compounds per year means that I'll get more money back on my investment. So should I choose this option because it's got more compounds So because we have the different rates of interest and the different number of compounds per year, it's actually really difficult to know which option to choose. And that's where the effective annual rate of interest formula comes in, which you've probably heard about. So the effective annual rate of interest is the annual interest rate that would generate the same amount of interest with one single compound per year as that generated by the original loan. So what we're asking is, what is the annual rate of interest that would generate me the same amount of interest if this loan or investment only had one compounding period? So for example, to compare these two options on equal footing, we'd say, well, okay, we know that 6.1% per annum compounding annually would give us a certain amount. But if we took the effective annual rate of interest, what that would do is this formula would practically, in essence, convert 5.95% compounding weekly. It's asking effectively what rate of interest would generate the same amount of interest as if we just had one compound per annum. And then by finding out that value, we can then compare the other values on equal footing. And this is a formula that we use for that. And M is the number of compounds per year in that formula there. So let's look at an example. So Sam borrowed $50,000 from the bank at an interest rate of 3.9% per annum. So that's his current rate of interest. And remember, he's borrowing it, so it's a loan. He doesn't want to pay back lots of interest. He wants the cheaper option. And it's compounding fortnightly. So we've got 26 compounds per year. And he makes fortnightly repayments of $600. But that's actually not relevant to this current question. The bank asks if Sam would like to instead have 3.8% per annum, which is a lower interest rate, but taking compounding weekly. So it would compound more often. So it's a lower rate of interest, which is awesome news, but it would be compounding more often. It would be compounding 52 times a year instead of 26 times a year. So how is Sam going to know which to choose? Should he accept this offer or stick with what he's currently doing? So let's use our effective annual rate of interest formula to determine that. So I effective. We'll have a look first at the 3.9% per annum option. So here you see that I is our decimal rate of interest, and you can see here in the I effective formula that it already takes into account the number of compounds per year. So I in the annual effective rate of interest formula is simply the decimal rate of interest per annum. That's all we need to know for that bit. So for his first option, the option he's currently on, it's 3.9% per annum, so 0.039, divided by the number of compounds per year, and because it's compounding fortnightly, that's 26, and then also to the power of the number of compounds per year, which again is 26. So the effective annual rate of interest, when we solve that and put it through the calculator, is 3.974% per annum. So effectively, if this first option was just to have one compound per year, this is the percent of interest per annum that would produce the same amount of money. So now let's do the same process for the second amount so that then we can compare them on equal footing and help Sam make his decision. So same formula, but here our decimal rate of interest is 0.038 because that's the other interest rate he was offered. And then our compounds per annum is 52 because he was also offered weekly compounds. So that's 52 times a year. Again, we solve it, we put it through the calculator, and that gives us an annual effective interest rate of 3.872. So the annual effective rate of interest for the second option he was offered is actually more beneficial for him because effectively, when we convert them both to annual per annum rates of interest, this one is actually lower, and because Sam is borrowing money, so it's a loan, so he's having to pay back this interest, then yes, he should accept the second offer because that is actually better value considering the fact that it's a loan. So I hope that made sense for that question, and hopefully Sam will be able to make some money back on that option. So yes, if I was Sam, I would definitely accept that offer because it's effectively a lower rate of interest, which is good news when you have a loan. But, so we've been talking about compound interest, but what if we don't want to wait until the end to pay my loan out? We've been talking about scenarios where we have a loan and the interest accrues over 2 years, for example, and then we've got this lump sum and then you pay it out. But what if, for example, we wanted to make monthly repayments instead, which is actually quite normal for loans in real life. People often make weekly or monthly or fortnightly repayments on a car loan or a house loan. And that gradually reduces the balance of the loan over time rather than just paying it out all at the end. And an interesting thing to note is that this actually tends to reduce how much interest you pay overall. So if you let it compound again and again and again and wait until the loan grows and grows and grows, and then you just choose to pay it out in one lump sum all at the end, that means you're actually probably going to end up paying a little bit more interest. Whereas if you make monthly repayments, the amount that they're charging interest on is slowly getting smaller and smaller, so you'll actually end up paying less interest overall in the long run, which is good news for a loan. So again, we can calculate reducing balance loans using recursion. So just like compound interest, we can use recursion. So what that is that's applying the same rule every time. So if you think about it conceptually, before I show you the formula, we have our initial amount, which is the money left owed on the loan, and then each time period, they're going to charge interest on that, and then we're going to make a repayment. So, and then in the next time period, they'll charge interest, and then we'll make another repayment. And how we model that using the recursive definition is this here, and you can see it. So the value of the loan after n plus 1 amounts of time periods is equal to the previous value multiplied by r, which is the rate at which it's growing, the compound interest rate, take away capital R, which is our monthly repayment amount, or our weekly repayment amount, or our yearly repayment amount, whatever like compounding kind of time period we're working with. So A0 is again the initial quantity of the loan. AN is again the amount owed after n periods. And R is equal to 1 plus I divided by M. So we're coming back to this first version of the formula that we used, where R is 1 plus the decimal rate of interest per annum divided by the number of compounds per year. And that gives us the amount the loan is growing by, So we've got those two variables defined the same. And then our capital R is the repayment being made at the end of the period. So there's our formula. So take, for example, a loan of $20,000. The initial value of this loan is $20,000, and AN is still the amount owed after n periods. And in the case of this loan, they are being charged 12% per annum, which is a lot of interest, and that's compounding monthly. So this person is going to want to pay off their loan as quickly as possible so they don't have to pay as much interest, because the longer you leave your loan, the longer you leave it unpaid, the more time that the bank or the lender has to charge you interest. So to calculate R, we've got our decimal rate of interest, which here is 0.12, so we've got 12%, and then divide it by 12 because we've got compounding monthly. And then that gives us our growth factor of 1.01. So our loan, the value of our loan is growing by 1.01 every time period because they're applying interest on it. And then we have R, which is 2,000, because that's the amount that we're paying back on our loan every month. So that's how much the value of our loan is going to reduce by. And so now we have the recursive definition. So we have AN plus 1 equals 1.01 multiplied by AN. Take 2,000 where the initial value was 20,000. And now we're going to have a look at how we would apply that formula. And another little important bit of information is that by using the recurrence relation, we can actually also work out the number of time periods required to totally pay off the loan. And also important to take note that we have rounded here. So if you did it in your calculator compared to whether you round each time, that is going to influence the final amount a little bit as well, because rounding does make a difference in our answers. So it's important to just keep track of whether you're rounding or not. So, okay, we're going to start by solving it. Let n equal 0. So you substitute into the formula n plus 1, 0 plus 1 equals 1.01 multiplied by A0, take 2,000. And that absolutely makes total sense, because what we're saying here is A1, so the amount after one time period, the amount after 1 month, is equal to our growth factor multiplied by the original amount. So the original amount is growing by that much, but we're also taking away $2,000 because we're paying off $2,000 of that loan. And so you can see here the effect of that. Our loan, how much we owe, has increased by $200 because that's how much interest has accrued. But then it's grown, but now it's going to shrink a little bit because we're going to pay off a little bit of it back. So the amount owed, left owing after one time period, is $18,200. So even though we've made a $2,000 repayment, it's not $18,000 left on our loan, because $200 of that has gone to paying off the $200 of interest that we've accrued. So as part of our money has gone to paying off the interest, and then the rest of the money has gone to paying off the loan. So it's interesting to note that imagine if this person had decided to make $200 repayments per month. Well, then the initial amount would grow by the factor. It'd grow to $20,200. They'd pay off $200, and then the next month the exact same thing would happen, because they would only be paying off the interest on their loan. They wouldn't actually be paying off the loan itself, which is quite a trap that some people fall into when they've taken out a large number of loans, because they might get stuck into just paying off the interest and not being able to afford to pay off any more. But that actually means that all their money is going to pay off the interest instead of actually paying off the loan. So the good news here is this person is able to make a sizable repayment every month, so that the amount they owe on their loan will actually be decreasing. So then we can apply the formula again. So amount after 2 months will be equal to the amount after 1 month, grown by the certain factor that it's growing by. And then again, we're going to take away the $2,000 because we're making another repayment to reduce the value of the loan. And then that will bring us down to a value of $16,382. And then we're going to do the same. So after 3 months, there's $14,545 left owing on our loan. And then after 4 months, and then as we continue after 4 months, after 10 months, we've worked out all the way to, I've set a ... there because we've done the working out, but we've just skipped over it. So after 5 months, 6 months, 7 months, 8 months, and now we're up to 10 months. So after 10 months, there is $1,168.20 left owing on their loan. That is awesome news. They've almost paid it off. They're only left owing $1,168.20, which is lower than the monthly repayment. They're repaying $2,000 a month. So we know that this month is going to be the month that they're able to pay out their loan. But this is a step that quite a lot of people forget to do because it's a little bit tricky to think about it in your mind. But what we actually need to remember to do is actually apply interest to this final amount, because it's not like the bank's just going to say, oh, don't worry about paying interest on the last one. No, our formula still applies. It's still the amount A11, so the amount owing in the 11th month, is still going to be this amount here, multiplied by 1.01, and then take 2,000, except it's not going to be 2,000. It's going to be whatever the amount left owed is. So we've got to make sure that we remember to apply the interest on this final amount. So what we did here, we took that final amount, multiplied it by 1.1 to work up the last little bit of interest, and that left $1,179.88 left owing. So their final repayment, their final adjusted repayment, some questions might call it, is going to be $1,179.88. So they're not going to have to pay $2,000 in the 11th month because there's not that much left owing on the loan, which is awesome news for these people. Throughout the process, if the investment rate or repayment amount changes, we can always change the value of I, R, and R. If they said, for example, after 5 months, they changed the monthly repayments to $1,000, we could take that into account in our recurrence relation, but we didn't have to worry about that here. Because we didn't have any changes. So it was nice and simple and straightforward. But another thing we can actually work out is how much interest did we pay. So how we can work that out is we can actually work out the total amount that was repaid, and then that will help us to find out the amount of interest that we paid back on our loan. So to work out the total amount, you would work out the total amount repaid. So to make that a little bit clearer, I'll go back to the previous slide. So we can see that up until the 10th month, we repaid $2,000 a month. So for 10 whole months, we paid back, or this person paid back $2,000 every month. So 10 months, $2,000 a month, mean they paid back $20,000. And then in the last month, they paid back $1,179.88. So we can see that the total amount they paid back was $21,179.88. And to find out the amount of interest paid, what we do is we take the amount paid back in total, which is this amount here, and take away the principal value from that. So we have $21,179.88, and we take away $20,000 from that, and that leaves us with $1,179.88. So we can actually see that that was the amount of interest paid, which makes sense, right? Because the total amount that we're paying back Part of that is paying off the loan, the money that we borrowed, but part of the money that we pay back also goes to paying off the interest. So we can see that $20,000 went back to just paying off our loan that we owed, but we can see that this amount went off to paying interest. So that's quite a lot of money in interest. And you can definitely imagine it would be even higher in the case of like house mortgages, for example. So that's how much money they paid in interest. And like I said, if you have a higher monthly repayment, you pay off your loan faster. So you actually end up paying less interest. Or if you make more frequent repayments, you also pay it off quicker. So you end up paying less interest total as well. So that's interesting to keep in mind. Oh, I think that was just what I covered. And just then, so like I said, the higher the interest rate, the longer it'll take to pay off the loan because we're being charged more interest with each compound. And also the higher the monthly repayment or weekly, fortnightly, yearly, whatever frequency the repayment is, the shorter the time we'll spend repaying the loan because we'll be reducing the balance quicker and we'll be charged less interest as it will be calculated off a smaller amount. And next little thing we're going to look at is when we want to calculate the monthly payment required, we actually use the annuities formula. So the formula we used back here, where's our formula? This formula here. We actually don't use this formula if we're trying to find out the monthly repayment. It doesn't work when we're trying to find out the monthly repayment. So instead, we actually use the annuities formula, which we're going to have a look at now. So annuities, before we explore the formula, what are annuities? So an annuity occurs when instead of investing one lump sum, such as in the case of compound interest, because in those kind of questions we just looked at, a lot of our questions were someone invests $50,000 and then lets compound interest apply. So that's kind of more of a compound interest scenario. But in the case of annuities, we periodically add a set amount of money to an investment. So for example, choosing to save $500 into an account every single week. So it's kind of like a reducing balance loan, except it's the exact opposite. It's kind of like a consistent savings account. So with a reducing balance loan, like you have this chunk, like this lump sum of money that you owe, and then every month, like you're paying off money to kind of pay off your debt. But with an annuity, it's an investment. So you're doing a similar thing. You're paying $500 every month, for example, but that's going into a savings account instead. So like the example I gave here is, for example, it's like saving $500 into an account every single week. So that's what an annuity is. We can also calculate annuities using recursion. You can see our formula here. Again, it makes sense. So it's, let me just pull up our other variables. So an plus 1, so the amount after n periods plus 1 is equal to r, the factor by which it's growing by each period, multiplied by the amount owed after n periods, but instead of minus r, which is indicating us paying off the loan, it's plus D, which is the deposit at the end of the period. So like I said, when we had the reducing balance loan, there was this sum of money, but our goal was to get it to zero because it was a loan. It was a debt that we had to pay off. But when we're talking about annuities, annuities are an investment. So we're actually adding to our investment every week, month, year, however often we're depositing. So our annuity is going to grow over time, and it's going to grow for two reasons. Firstly, because of plus D, because we're depositing frequently at regular intervals into an annuity. And then it's also going to grow because of R, which is the factor by which it's going to grow. So in reducing balance loans or any type of loans, compound interest works against us. Interest grows, and that's really frustrating because then we have to pay it off. It's not a great thing. But when we're talking about investments or annuities, for example, interest is an awesome thing because interest is increasing how much money we have. So interest is like literally being added to their bank account because they've got their money in that account. So that's why an annuity is going to grow, because we're going to get interest paid out on the money that we have in that account. And also we're going to add to that account regularly. And then, A0, AN, R are all defined the same here as what we've talked about before. So let's look at an example, do a question. So again, let's look at an example of an account with $20,000. But this time, it's not a loan of $20,000. Think of it like $20,000 in a savings account. Here we have an 8% per annum interest rate, and it's compounding quarterly. So that means our R, our growth factor of our investment, is 1 plus I over M, decimal rate of interest, 0.08, divided by number of compounds per year, compounding quarterly, so once a quarter, so 4 times a year, gives us our growth rate of 1.02 per quarter. So it's going to grow by 1.02 every quarter. And D, this person in their annuity, they are going to invest or add to it $5,000 every quarter. So let's use our formula. So A, n plus 1 equals 1.02 AN plus 5,000, where A0 is equal to $20,000. So our starting point isn't 0. Our starting point, we're told, is $20,000. There was already $20,000 sitting in this account before this question started. So when we apply the rule the first time, so after 1 month, we will have interest applied to this amount that was already in the account, $20,000, and that's obviously the interest, the growth factor. Then we also have the plus $5,000. That's this plus D. That's the amount that's being deposited into the annuity every quarter. So you can see that after 1 quarter, or one quarter of the year, our time period, the amount in the annuity is $25,400. So we can see that $5,000 of that growth has come from the deposit. We can see that $400 of that growth has come from the interest. And if we apply the formula again to get A2, we'll see that we have $30,908, and then A3, so after a third quarter, and then A4 after a fourth quarter. So that means in this annuity, we'd have $42,256.68 after 1 year, because we started with $20,000, and then each quarter we added another $5,000. So adding $5,000 4 times throughout a year, we add $5,000, then we'll have $10,000 added, then we'll have $15,000 added, and then we'll have $20,000 added. Shows us how we get this final value. So we started with $20,000, we added $20,000 over the course of a year, and then that means $2,256.68 is a result of interest. So they've actually earned like over $2,200 in interest, which is awesome news for this person. So you can kind of see how an annuity is like the exact opposite of a reducing balance loan. A few things to note. So usually with annuities, the objective is to continually invest money until a certain threshold or goal is reached. So for example, it might be you're saving for a holiday or a house deposit or something. So a person might decide, I'm going to save $100 a week into this account, and when it reaches $20,000, then I'm going to take it out and buy my house, or like put down a deposit for a loan on a house. So that gives annuities a sense of duration. And by like duration, like what we kind of just discussed, we're kind of referring to like how long the annuity is going to go for. You could leave it forever and add $100 a week every week forever, but most of the time that savings would have a goal. Like we said, for example, a holiday or a down payment for a house. And I think we've already briefly touched on that there are ways that we can affect the duration of the annuity. So for example, a higher interest rate will result in a lower duration because we're going to be gaining money quicker. Again, this is an investment. So we're investing money. So if we have a higher interest rate, the amount of money that is ours is going to grow quicker and quicker and quicker. And that is really awesome news because we want to make lots of money from it. So we're going to reach our savings goals quicker. So it's going to have a shorter duration, you could say. Or if we have a higher periodic deposit, so no, I'm going to save $200 a month instead of $100 a month. That higher deposit, it'll also reduce the repayment because again, we're adding more to the investment. We're going to reach the end goal quicker. And again, that is quite literally the opposite of what we learned in reducing balance loans, because this is an investment rather than a loan. So annuities, there's also the annuities formula, or the annuities future value formula, which is again the case where we don't have to use a recursion. And this is what we have here. So to define our variables, A is the amount in the annuity. So we're still talking about annuities, but this is just the formula instead of using a recursion. M is the periodic deposit. So for example, $200 a month. I is the decimal interest rate per period again. So if it was 8% per annum, I would be 0.08. N, number of compounds. And then the annuities future value formula is asking the question, how much will our regular investments of M, how much we're periodically depositing, grow to after N time periods? So how much money is pretty much what's our future value going to be of this annuity if we keep investing this amount of money over this amount of time? And the interesting thing to note is that this formula only works if the initial value is $0. Otherwise, we need to use the compound interest formula as well. And that's because if we have, for example, an initial value of $20,000, we can't just add on the $20,000 at the end, and this formula doesn't take into account the $20,000 because interest would also be being applied to the $20,000. So we'd have to think about, well, okay, how much are we earning from this, but also how much compound interest would we have earned on our initial value as well. So let's do a question to demonstrate that. Suppose we have an initial balance of $30,000. Interesting, we're going to have to use the compound interest formula as well as the annuities formula. And we deposit $1,000 at the end of every month. So we're looking at monthly. And interest is compounding 6% per annum. How much will be in the account after 5 years? So we have our annuities future value formula. We know that M, the periodic deposit, they're adding $1,000 every month. We also know that I, the interest rate, is the decimal rate of interest, 0.06, divided by the number of compounds, monthly, 12 per year, gives us 0.05. You can see also the 1 is built into the formula here as well, so we don't need to add the 1. Then we have N, the total number of compounds. So we have 5 years, 12 months a year, so we've got 60 compounds in total. And then from there, we can just substitute into our formula. So we have A equals 1,000 and the rest of our numbers that we've substituted nicely in. And the awesome thing about calculators is they can solve equations like this for us. So the future value of this annuity is $69,770.03 because they invested $1,000 every month for 60 months. So you can see that's where the $60,000 came from. And then the $9,770.03 is the interest that they would have earned from that. But off the back of what I said earlier, this would assume that there was no money in the annuity to begin with, but that's not true. So this is why we need to use the compound interest formula as well. So back to our friendly compound interest formula. So we have our initial value was $30,000 and it's growing by a factor of 1.005 and it's going to do that 60 times over. And that gives us $40,465.50. So you can kind of see there's these two elements here. This is the money from our regular periodic deposits plus the interest based on that. And this is our initial amount, $30,000, plus the almost $10,500 of interest that they've gained on that initial amount. So to get the actual true, fully everything included final value of our annuity, we've got to take into account this value here and this value here, which will give us a total of $110,435.53 after 5 years. So that's why when we have an initial sum in an annuity, we need to consider both the compound interest formula and the future values annuity formula. So I hope that one made sense for you. Another trial exam question. So a plumber wants to invest his earnings into a fixed term account. He opens the account and deposits $2,300 per quarter, 2.86% per annum, compounding quarterly. how much will be in the account after 5 years. So this sounds like a perfect scenario for the future value of the annuities formula. This is almost exactly what we did before. The future value is unknown. We know that M, the deposits he's making every quarter, is $2,300. So we've got that sorted. We know that I is again 2.86 divided by 100, and then we're also dividing by 4 because it's quarterly compound, so that's like our M value, and that gives us our decimal rate of interest. And then we can substitute into the equation, and that'll give us our answer, and we can see that that is $49,262.76. So that's how I'd use the future values annuity formula to solve this question. So that's pretty similar to what we just did before. But our next question, what if our annuity went on forever? And if we wanted to receive a certain amount of interest based on a once of fixed deposit? So have you ever thought about, for example, what if I won the lotto and just put the money in an awesome bank account and just lived off the interest? Have you ever thought about that? I definitely have. I think that would be awesome. Well, the awesome thing is, if you have considered that, or if you now have considered that, that's pretty much a perpetuity, which is what we're talking about. So I like to think of it like a perpetual annuity. It's like an annuity that goes on forever. It kind of has like an endless duration. So what a perpetuity is where a fixed amount is placed in the bank. So like me putting my lotto money in the bank, if I ever win, or if I won, or if somebody won, so that would be placing that fixed amount in the bank, or that might be a savings or an inheritance, or that could be any kind of sum of money. So where that fixed amount is placed in the bank, so again, that's our initial deposit, and then the interest is calculated per period, and then the interest is taken out and paid to or withdrawn by the owner. So what we're having here is we've got this lump sum, then interest is earned, and then I take the interest out. Next time period, interest is earned again, and I take out the interest again. So every single time it's coming back to the original value because all I'm doing is taking out the interest again and again. And don't worry, the formulas for perpetuities are much, much simpler. It is simply P equals D divided by I, where P is that initial amount deposited, so for example that lotto money. D is how much you gain or withdraw every period, and I is the interest rate. And again, we can rearrange this formula to identify a different unknown. So the question that we're looking at here, for example, say we deposit $10,000 into an account gaining 5% interest per annum with semi-annual compounds. What is the semi-annual payment received by the owner? So we're calculating, again, our decimal, we're calculating I here. We've got our decimal rate of interest, 5% per annum, 0.05 divided by 2, because we've got semi-annual compounds, so twice a year. That gives us an I of 0.025. And we know that P, the principal, the amount they initially deposited, was $10,000. So now we can substitute P, $10,000. We don't know D. That's what we're trying to find out. What payment are they going to receive? And we know what I is, 0.025. So what we then do is we can solve and isolate. We can multiply both sides by 0.025. We can solve for D, and that'll give us $250. So that means if we had $10,000 in that perpetuity, in this scenario, that means every 6 months, so twice a year, it would produce $250 of interest. They would take out that interest, and then it would go back to $10,000. Then 6 months later, it would produce another $250 of interest, and then they'd take it out again. So that person is taking out that $250 of interest every 6 months. And so that's how they kind of ended up in this perpetual annuity kind of situation. And we could also rearrange the formula to solve for P or I, depending on the question. Amazing. I know I spent a little bit longer on that section than I was expecting to, but I feel like we've done a really, really thorough job of covering loans and investments. And I know financial maths can definitely be a bit of a struggle and a confusion for some people. So I really hope that's helped clear things up a little bit. Good work. We've made some good progress today. Again, feel free to pause or take a break if you need, or ask any questions that might have popped up in your mind in the chat box. But for now, we are going to keep moving on to graphs and networks, which is topic 2 of Unit 4. So loans and investments, which is topic 1, is generally very formula heavy. So I gave your brain so many different formulas to think about when we covered that. Graphs and networks is a little bit different. It's not so much formulas, it's more like definitions and understandings. So that works better for some people and that's trickier for some people. So whichever way that is, we're gonna get into it. So graphs and networks. To kind of simplify the confusion, graphs and networks, they're pretty much the same thing. I'll give you the slightly different definitions later, but they're pretty much just referring to the same thing. So this is an example of a graph or a network. So a network, graph, or diagram represents the connections between objects. So that's, in essence, the summary of what we're looking at. It represents the connections between objects. Here we can see that this line connects B and G, this line connects A and F, and it's comprised of edges and vertices. You can see the vertices are like the points, and the edges are the connections. So for example, this graph or network here, it could represent connections between friends, it could represent who knows who, it could represent trains connecting different towns. There's a number of different things they could represent. They could represent almost anything where there's connections between different things. So a graph refers to a structure formed with edges and vertices. So for example, this is vertex H, this is vertex A, this is an edge connecting those two vertices. So like I said, vertices are the points and the edges are the connections. And technically, a network refers to a graph in which the edges and vertices have some special meaning attached to them. So they're very similar definitions, so we use them interchangeably. So technically, if this did not have any meaning associated with it, technically it would be a graph. But if this represented connections between different towns, then it would be a network because it's got a special meaning associated with them. But again, we very much use them interchangeably because they're very similar definitions. So to practice applying that knowledge, how many vertices does this graph have? And remember, vertices are the number of points. And if you've counted them, A through H, you would have seen that there is 8. Question, how many edges? We can see that there's also 8. And you can also note that they don't all have to be straight. This one is a curved one, for example. So edges don't have to be straight. And another thing I'd love you to notice is that B and G are connected by 2 different edges, and that's called having multiple edges, when there's multiple edges connecting the same vertices. And finally, we have an edge that starts and ends on the same vertex, and that's called a loop. And that's, for example, what we have on vertex C here. So, more terminology. What is the degree of vertex F? And hint, remember that the degree is the number of edges that meet or leave the vertex. And that would be 2. If you can see here, we have, what do we have, F? We can see that there are 2 edges connected to vertex F, so it's got a degree of 2. What about the degree of A? You can see it's got 4 edges connected to it. What about the degrees of D and H? Well, it's actually 0. They're isolated vertices because they have no connections to any of the other vertices. And another thing that's really interesting is that C actually has a degree of 3 because it's got this edge here, but it also has a loop. And a loop actually adds 2 to the degree of a vertex. So it can be helpful to think of the degree as the number of different ways you can leave a vertex. So it's important to note that a loop adds 2 to the degree of the vertex. What about these ones here? So this one on the right is actually an example of a subgraph of the original graph. So what is a subgraph? It's essentially any graph you get when you remove edges and or vertices from the original graph. So some information is removed, but no new information is added. So it's part of a larger graph, but again, there's no new information in a subgraph. And so you can see that E was removed and all of its connected edges and the loop on C and both isolated vertices. So we can see that that information was taken away, that nothing new has been added. A simple graph has no loops and no multiple edges. And note that this is actually also a subgraph of our original graph. We've just had some parts taken out to make sure that there is no loops and no multiple edges. So we've turned it into a simple graph. A complete graph is where every vertex is connected to every other one. You can see that here our two vertices are both connected. Here all three vertices are all connected to each other. All four are connected and all five are connected here. And another interesting thing to note is that all complete graphs have n bracket n take 1 divided by 2 edges. So that can be a helpful formula if you ever need to apply that in a question. So another type, we can also have weighted graphs. So that's when an edge has a weight associated with it or a number linked to each edge. And that number could represent a different thing depending on the graph. It could represent the number of liters that could flow through a pipe. It could represent the number of cars, of traffic that could pass through a certain area. It could indicate the road length in kilometers. These weights have a meaning or an association in the network. So we have an example of that here. You can see that this edge here has a weight of 5. This has an edge of 3. We're not told here what it means, but we can see that it does have weights. We can also have a directed graph or a digraph where edges have a direction associated with them. And this can help us model and communicate the direction of something. That could be water flow, traffic flow, different things. And digraphs, so a graph with direction associated, can also be weighted. And edges in a directed graph are known as arcs, and the direction is shown by having an arrow on the arc. So here you can see that there is a one-way connection from G to B, but we also have a one-way connection from B to G. You can see we have a one-way connection from A to C, but you actually can't get back to A. It's only a one-way direction. So that's interesting there as well. So let's have a talk about the adjacency matrix. So what is an adjacency matrix? An adjacency matrix would look something like this, except it would be filled in with numbers. And it is like a matrix, which you would have covered in year 11, that records how many edges connect each vertex. And note also as well that this is a connected graph because everything here is connected. We don't have any isolated vertices. And another quick thing I'll draw your attention to is what is an example of a bridge. That's some more terminology you might need to know. A bridge could be this one here, for example, this one here, for example, or this one here. Oh, not that one there, actually. Sorry, that's my mistake. That's not a bridge. But this is an example of a bridge, and this is an example of a bridge. And I'll leave it to you to think about why. So coming back to the adjacency matrix, it records how many edges connect each vertex. So let's think about the number of connections between A and A. Well, there's nothing that connects A to A. A to A is the same vertex and it doesn't have a loop, so there are 0 connections connecting A to A. What about connecting A and B? Well, I see one edge, so we have one connection between A and B. How many connections between A and C? 1. How many connections between A and D? Actually, no direct connections, so we have 0, and we can actually fill in the rest of the graph. Some interesting things that I'll draw your attention to here is the connections between B and D. Connections between B and D is represented here and here. You can see that it's 2, and that indicates again that we have our multiple edges there. You can also see that C connected to C has 1 because this is a loop there. So there is one connection between C and C. whereas none of our other vertices have a loop. You can also see that adjacency matrices are actually symmetrical down their leading diagonal. So an interesting check to see if you've gotten it right there is to check if it is symmetrical down that leading diagonal. So in a directed graph, we can actually also have an adjacency matrix for a directed graph, but it will look a bit different and it likely won't be symmetrical down the leading diagonal, because in a regular graph, the connections go both ways, but in a digraph, our connections are only one way. So they're not two-way streets, they're only one-way streets. So we only count the connection in the direction indicated. And we do this by assuming that we're counting the edge from the vertex stated by the row and to the vertex stated by the column. So to illustrate that, I've added our little labels here. So you can see here that A and C are connected, but we can see that it's a connection from A to C, not the other way around. So from is always indicated by the rows and to is indicated by the columns. So we can see that from A to C, we have 1 because there is that one edge connection from A to C. But if we have a look at, even though there is a connection there, if we look at from C to A, we can actually see that it's 0, and that's true because even though there is an edge there, it's a directed edge going in one direction, so it's only going from A to C. We can see, for example, that these multiple edges connecting B and D, one goes in each direction. So B to D is connected and D to B is also connected. So feel free to have a pause of the video and have a look at some other of the numbers if you'd like to explore a little bit more how they work. Alright, I'm going well for time. So, construct a network that represents the Facebook connections between friends and then construct an adjacency matrix to represent this. So first we're told that friends on Facebook work both ways. So if person A is friends with person B, then person B by default is friends with person A. So that tells us that we do not need a directed graph because the connections go both ways. Whereas if we were talking about Instagram, for example, we would be using a directed graph because we would say, will they follow them? But do they follow them back? So we'd end up with that directed graph. But here we're talking about the both way connections. So the people we're talking about are Samantha, Jacob, Eliza, and Peter, and we're modeling their connections on Facebook. So Jacob is also friends with Eliza. We have Samantha is friends with Jacob, Eliza, and Peter. And a person can't befriend themselves on Facebook. So that tells us that we can't have any loops. And the network, like I said it doesn't need to be directed because the connections go both ways, and it doesn't need to be weighted because there's no weight associated with it. A connection represents just the presence or absence of a friendship on Facebook. So how I'm going to draw this graph is I'm going to draw a vertex to represent each friend. One for Jacob, one for Eliza, one for Samantha, and one for Peter. And then I'm going to draw in edges to represent the connections between each friend. So I'm going to start with our first bit of information. So I can see that Samantha is friends with Jacob. So I've connected S to J. Samantha is also friends with Eliza and with Peter. So there, I've modeled our first bit of information there. And it doesn't matter if you set up or structured your graph or network in slightly different way, as long as it's displaying equivalent information with the correct vertices and the correct connections between the associated people, then that means that the graph or network is displaying the correct information, which is the most important thing. So next we can see that Jacob is also friends with Eliza. So I'm going to add a connection from J to E. And we know that a person is not allowed to befriend themselves on Facebook, so we have no loops. So we can see that there is our graph or network. And then we're also told to construct an adjacency matrix that represents this. And because it's not a directed graph, we don't need to worry about from and to, because all of these connections are two-way streets because we're talking about Facebook friends. And so that makes it a little bit simpler. And then we also know that it's going to be symmetrical down the leading diagonal. So S to S 0 connections there because we have no loops. Samantha can't befriend herself. But we also know that Samantha is connected by 1 connection because that's the maximum we can have here because you can't be friends multiple times. Samantha is connected to Jacob, Eliza, and Peter. So we can fill that in. And then we can also fill in the rest of it. So we can see that Jacob is only connected to Eliza and Samantha. So we can see there's a 1 for Samantha and Eliza, but a 0 for the other people. Eliza is connected to Jacob and Samantha, and Peter is only connected to Samantha. And we can also see that again where it's symmetrical down the leading diagonal. So that's our adjacency matrix. So identify the vertex that contains a loop. Identify 2 vertices that have multiple edges. Identify the isolated vertex and identify a bridge. So the vertex that contains a loop, I'm sure you can see, would be E because the edge is connecting from E straight back to itself. Can you see 2 vertices that have multiple edges? Potentially you identified A and D because you can see there's 2 edges connecting those 2 vertices. The isolated vertex would be G here, and the example of the bridge would be the edge connecting D and E. And I touched on bridges earlier because if we took away this edge, if we took away this connection, then our graph, it would actually separate the graph entirely. So it would no longer be all connected. G is actually already isolated by itself, so it already did have an isolated element of this graph. But if we did take away this bridge, we'd have those 2 separate areas again. Now we are going to be talking about planar graphs. So before we move into planar graphs, we'll touch on equivalent graphs first. So equivalent graphs or isomorphic graphs contain the exact same information. It's just rearranged or displayed in a different way. So when I was talking about our subgraphs, we had that some information had been removed, but nothing had been added. But when we're talking about equivalent graphs, they contain the exact same information, just in a different form. For example, have a look at this graph here, and then have a look at this one here. These, well, they look different, and they are different in some ways. They actually display the exact same information and connections because they're equivalent or isomorphic graphs. Because we can see that this connection here has simply just been stretched and moved around to the outside. So planar graphs are graphs where no edges cross over each other, or there is an equivalent graph where there are no overlapping edges. So this graph technically is a planar graph because there is an equivalent graph where there are no overlapping edges. It is just not in a planar form here because these edges overlap. You can see that intersection, that cross section that we've got in the middle because the edges are crossing over each other. But here we do have an equivalent graph where there are no overlapping edges. Where if there was not an equivalent graph with no overlapping edges, then it would be a non-planar graph. It would not be a planar graph. But these graphs here are technically both planar because this one has an equivalent form where we can make sure there are no overlapping edges. So what can we notice about this graph? We can see we have 4 vertices. You can count the blue points. We have 4 vertices, 1, 2, 3, 4, 5, 6. We can see that we have 6 edges. The other bit of information that we can find out from here is that we have 4 faces. So what is a face? A face is like a defined or distinct enclosed separate region of a graph. So that is an example of a face. That is an example of a face, as is that. And it's also important to remember to consider the outside area as well, because that's another distinct region of the graph. So we can see here that this planar graph has 4 vertices, 6 edges, and 4 faces, which brings us to Euler's formula, which you might have heard of. So Euler's formula for planar graphs tells us about the relationship between the number of faces, edges, and vertices of a planar representation. So Euler's formula is only relevant and only applicable to the planar representation of the graph. And Euler's formula is V plus F, take E equals 2. or the number of vertices plus the number of faces minus the number of edges equals 2. So Euler worked out the exact mathematical relationship between the number of vertices, faces, and edges for any planar graph, and this is what they found out. And we can actually see that that does hold true in this planar graph. Number of vertices, we have 4. Faces, we have 4. Edges, we have 6. So 4 plus 4 gives us 4 plus 4 gives us 8. Take away 6 gives us 2. And because 2 equals 2, we know that Euler's formula does hold up in this situation. So we've talked about a whole bunch of different things, and now we're up to the idea of walks. So walks are the idea that you can actually move around a network. So I could move from this point to this point along this edge. I could move along this edge. I can move around and around on the edges. So the idea that we can move around the networks is often referred to as like walks. And there's certain language that we use to describe those certain movements. We have open and closed walks, open and closed trails, open path, we have cycles. We can look for the shortest path weight-wise. There's all of these different things we can do, all of these different ways we can move around a graph or a network. And my challenge for you is to construct your own glossary of definitions with examples to solidify your understanding of these differences, because we're not going to go through them today. So make sure you get that clear in your mind, because that can be really good, easy marks for short answer or multiple choice questions in an exam. So one thing I did mention that we are going to go into in a bit more depth is looking for the shortest path. And when I say shortest, I'm not talking about the shortest number of steps. I'm talking about the shortest weight-wise. So we want the lowest weight, whether that's the lowest cost, the lowest time, the lowest amount of kilometers. We're looking for the lowest weight. So like I said, when we're talking about the shortest path, it would probably actually be more accurate to say like the lowest weight. Because for example, we're going to be talking at the moment, we're going to be looking at finding the shortest path between two different vertices. First, from B to E, and secondly, from B to G. So let's take B to G for an example. We can see that we have one edge connecting B to G. Because it has one edge, it might appear to be the shortest path, but that has an associated weight of 15, we can see here in our graph. Whereas if we took a different route that might potentially have more steps to get to B from B to G, but would it have a lower weight? That's what we're asking. So let's have a look at for B to G. So B to G possible path options. We could start from B, go to A, go to F, and then go to G. And because they both, even though there's multiple edges connecting F and G, because they both have a weight of 1, we could actually take either of these options. So it doesn't matter which. So they both have a weight of 1. So taking that path from B to A to F to G, that has a weight of 3 and 9 and 1, which gives us a total weight of 13, which we can actually see is already a lower weight than doing 15. So what's our next option? We could go from B to C, over to F, and then again over to G, which has a weight of 6 and 3, and then also 1, which gives us a weight of 10, which is actually even lower than our first option. And then we also, like I said, have that option of going straight directly from B to G, and that has a weight of 15. And because we are looking for the shortest path, or like the shortest path as in lowest weight, we can actually see that B to C to F to G is actually the best option because it minimizes the length, weights, liters, whatever it is that this network is representing. It has the lowest weight, so that is actually the quickest or most efficient or most cost efficient route, even if it seems like B to G via this edge here would be quicker because it's simply one edge. But when we're talking about the lowest weight, that's actually not accurate. So that's interesting to keep in mind as well when we're talking about the shortest path. We're not talking about the shortest number of steps or the shortest amount of edges. We're actually talking about the lowest weight. So if a connected planar graph has 8 edges and 6 vertices, how many faces does it have? We actually don't even need to be able to see or need to draw this to work this out. And that's because of, I hope you remember, Euler's formula, which states that the number of vertices plus the number of faces minus the number of edges will always equal 2 in a connected planar graph. So we know that we have 6 vertices. We don't know the number of faces. That's our unknown value. And we know that we have 8 edges. So all that we need to do then is substitute into our formula. And we can see that 6 take 8 will give us -2. And then to isolate f by itself, we add +2 to both sides. And that tells us that a connected planar graph with 8 edges and 6 vertices will have 4 faces. So, decision maths. We are on to topic 3, which is awesome news. And the even more awesome news is that maths is actually quite practical, and we get to see that side of it in this topic. We've already made it to topic 3, so awesome. Good work, everybody. We've made great progress today. So, for example, when we talked a little bit about, I talked a little bit earlier about when I talked about the shortest weight or the shortest path, I talked about how we wanted to find like the most efficient route. So we're going to be exploring some more techniques and questions and things like that, and a few other things as well when we're talking about decision maths. So we could be talking about like the most efficient way to do a project. We could be talking about like maximizing traffic flow, finding the most efficient plumbing solution. There's all of these different things we can do. So we're going to have a look at it now. So we're going to introduce another definition. We're going to talk about another type of graph. And these special type of graph are called trees. So what is a tree? A tree is a connected graph in which we have no cycles. So this means we have no loops, no multiple edges. It must be planar, so it can only have one face. And trees will always have n-1 edges. So I feel like trees kind of look like spiky, like scarecrows or skeletons. Or you can almost think of it like a tree without its leaves. Like it's the bare minimum, most simplest graph where every vertex is connected, because trees must be a connected graph. And we also want no cycles, which means we can't have multiple edges, we can't have loops, it must be planar, and it can only have one face. Because as soon as we added another edge there, that would actually introduce the presence of a cycle, and that would also mean we have 2 faces, so it would no longer be a tree. And because of this, we can also always know that trees are always going to have n-1 edges, which can be very handy to know. And we can see I've got a few more examples here. It could look like that, or it could look like that. Trees can look like different things as long as they hold to these definitions. But what about a spanning tree? So a tree does not need to include every vertex of the graph. It just has to be connected with no cycles and no loops, no multiple edges, all of that. So a spanning tree of a graph is a subgraph, which we talked about earlier, that is a tree involving every vertex. So a subgraph, so some information removed but nothing added, but it does need every vertex. So a spanning tree means that some edges have been removed. And then to make our definition a little bit more specific, a minimum spanning tree is the spanning tree of a weighted graph with the total minimum weight. So we're coming back in a little bit more to what I mentioned earlier with almost like the shortest path, except here we're not talking about like path. We're talking about the minimum spanning tree, which is the spanning tree of a weighted graph with the total minimum weight. So we want to connect every edge in, we want to connect every vertex in with the absolute minimal number of edges, so with no loops, no cycles, no multiple edges, so that we can get the total minimum weight, so that we can have the most effective project, road, plumbing project, whatever it is our graph is representing. And some can actually have multiple different minimum spanning trees. There could be a few different solutions that could help us get the total minimum weight. So that's important to keep in mind as well. And how do we find the minimum spanning tree? We do it using Prim's algorithm, which when you think it through is actually a very, very logical process. So what you do to do Prim's algorithm and find the minimum spanning tree of your tree or your graph, you pick a vertex. You can be any. You can literally pick any vertex and Prim's algorithm will work, and that'll be your starting point. And then you select the edge connected to that vertex with the smallest possible weight. And then so now you've added in another vertex and you'll have one edge connecting those two vertices. And that edge will have the smallest possible weight. And then now what you're going to do is move around the rest of the graph, connecting in every single vertex by using the smallest possible weight. So you keep adding edge after edge with the smallest possible weight. So you add another edge that's connected to one of the vertices that's already in your graph and also has the smallest weight. So every time you're connecting in a new vertex, but adding the minimum weighted edge, and that doesn't introduce a cycle. Because if the minimum weighted edge introduced a cycle, well, we could add it, but that wouldn't actually help us or serve a useful purpose because it wouldn't be part of the minimum spanning tree because it would introduce a cycle. And then you simply continue until every vertex is connected. So connector problems are all about finding minimum spanning trees. So for example, what's like the most efficient way to connect a group of towns by highways or like roads or trains? It could be about finding the minimum spanning tree to find the most effective way to do an electrical wiring setup in a house. Or it might be about solving a plumbing problem because again, the goal is to find the total minimum weight. So it might help us find like the most cost-effective way to solve a problem. Or like connect towns in the cheapest way possible with different roads. So these are all like different problems they can help us solve. So let's have a look. So this graph here represents possible roads that could be built to connect various towns. So here, our vertices are different towns in a certain area, and our edges are possible roads that could be built to connect the towns, and the weights or the numbers associated with the edges represent the number of kilometers apart that the towns are. So the question is asking us is what is the smallest length in roads possible to have all the towns connected? Is the minimum spanning tree going to have a total weight of 55, 56, 58 or 59 kilometers? Let's apply Prim's algorithm. So what I'm going to do is I'm going to start with the vertex in the bottom left-hand corner. And I'm going to see that I've got two edges attached to it, one with a weight of 2 kilometers and one with a weight of 3 kilometers. The most effective, the most minimum cost-effective way to connect in this vertex is by building that road there. So we're applying Prim's algorithm. Okay, so now my graph has two vertices, like the Prim's algorithm step said that it would. So now I've got to find the next most efficient way to add in another vertex. If I added this one, it'd give us a weight of 5. This one would give us a weight of 5, but connecting in this one would give us a weight of 3. So I'm going to choose to add in that one there. Awesome. Now I've got 3 vertices in my tree. All right, to add in another connection, I could add this, which is a weight of 10. Not ideal. Weight of 7, still a lot. Or we have the options of 5 or 5. And out of those options, 5 is definitely the lowest weight. So we're going to add in one of the 5s. And because they are the same weight, it doesn't matter which 5 we add in. So I'm going to choose to add in that one. And then I'm going to continue doing this exact same process, moving around my whole graph. So I can see that every edge connected to all of these, the next lowest weight would be this one here, connecting in that vertex because it has a weight of 3. Next, I'm going to connect in the vertex next to it by that root of 4. And then this is where we come to a bit of an interesting decision. If I look at everything connected to all of these different things that I've got in my graph so far, I can see that my lowest weights are 5. And before I said earlier we could connect in either 5 because they were the same weights. But even if this weight here was a lot lower, there would be no use adding this one here because it would add a cycle. So it would no longer be a tree, and it also is completely unnecessary because both of these vertices are already connected into our graph. So I actually don't even need to worry about building that road because we're trying to build these roads the most cost-effective way possible. So if I want to get to this town from this town, all I have to do is go that way. It would definitely be more efficient to have a road there, but it's cheaper to only build the minimum amount of roads. So that's the goal of this project. So the next thing I'm going to do is add that center vertex by that road of 5. And then I'm going to keep moving around my graph by using the same process. My next lowest weight is 6 by that one there, that connection. Then my next lowest weight will be that one there. And then as I keep adding them, if you want to pause or slow down the video to see the order that I've done it in and the thought process behind each connection, you totally can. But that is the process that I undertook. So what we do next is we add the weights of the edges in our minimum spanning tree to find the minimum weight in kilometers that's required to connect all the towns. And the answer is 59 kilometers. And if I actually take away the picture from behind our minimum spanning tree, it actually gets even clearer. Like that is so clearly a tree because you can see we have no cycles, no loops, no multiple edges. It literally looks like that skeleton or like that dead tree with no leaves. It's the bare minimum number of connections between all of our towns with the lowest minimum weight. So the most effective, most cost efficient, easy possible way we can connect all the towns is by having to build 59 kilometers of road. And to check our answer, we can also use the equation to make sure we added the right number of edges. So number of edges in the minimum spanning tree, number of vertices take 1. We have 17 vertices and I've added 16 edges, so we can tick that off. We know that we've done it right. So that's an example of using Prim's algorithm to find a minimum spanning tree and solving a connector problem because we've found the most efficient way to connect all of our towns here. So which of the following represents a tree? A graph with 14 edges, 5 vertices, 12 edges, 10 vertices, 6 edges and 7 vertices, or a graph with 11 and 11? So C, we can actually see is correct if we use that little rule that we talked about earlier, because we said that a tree of n vertices will always need n take 1 edges, because that's the number of edges required to connect in every vertex without introducing loops, multiple edges or cycles. So by using that formula, we can solve a question like this one here. And I could draw that to illustrate it. And again, it could be any type of equivalent graph and it would illustrate the point I'm trying to make. So we can see here our graph has 6 vertices, 1, 2, 3, 4, 5, 6. 7 vertices, 1, 2, 3, 4, 5, 6, 7 vertices, and we have 6 edges connecting them all. So we can see 1, 2, 3, 4, 5, 6, and we can see that that's a tree. But as soon as you introduce an extra edge, it actually no longer becomes a tree because we've introduced a cycle. So we can see here even by visually drawing it, not that we need to, that is our correct answer. So large projects. So we're going to talk about project planning. So large projects are usually broken down into many smaller activities or tasks that need to be completed one at a time. And sometimes the next activity can't begin until the activity beforehand has been completed. So when we're talking about project planning, we could be talking about building a house or making a cake, any sort of activity that can be broken down into any sort of subtasks. So if we're talking about making a cake, for example, my steps might, I got to, put all the ingredients in, I've got to mix it, I've got to pour it into the pan, I've got to put it in the oven to bake. But there's this idea here that some activities can't begin until the next activity before the activity before has been completed. So I can't mix my cake until I've cracked the eggs. I can't put my cake in the oven until I've poured it into the pan. So there's the idea that some activities require certain other activities to be completed first in order for us to be able to successfully complete the project. And this is where we can run into scheduling problems and we could waste a lot of time and money. Because if, for example, we were building a house and we had the people rock up to put the frame up with, the concrete guys aren't coming for 5 hours, then the people that have come to put the frame up are just going to have to sit around and waste their time because we weren't organized enough to make sure that the concrete was done first. So that's the idea of like a scheduling problem. Because we want to find the most efficient way to do our projects. And that's what critical path analysis is all about. It seeks to find out what activity needs to be completed by when, so that we can do everything in the least amount of time to maximize efficiency. So this is an example of a path here. Sorry, not a path, a project here. So we see writing header file A, writing header file B. These are all the different activities that need to be done. So this project is about designing some sort of software, and these are all the little individual sub-activities they've broken it down into. You can see that in this activity table, it also lists the time taken for each activity, and this column here is about the immediate predecessors. So this is about what activity must be completed before each activity so that the next activity can begin. So here we can see that activities A and B, so writing the header file A and B, don't have any immediate predecessors. That means they can be completed right at the start of the activity. And then when you look down to activities C and D, coding implementation for A and coding implementation for B, you can see that they do have immediate predecessors. They have activities that must be completed before these activities can begin, because you can't do the coding implementation before you write the header files. I don't know what that means, but I can tell that this has to happen before this, because I've been told that A is an immediate predecessor for C and B is an immediate predecessor for D. So they have to happen before the next activities can start. You can see again how we're going to run into scheduling problems if we don't make sure that that runs smoothly. And this is actually a graph or a network that represents this. So I want you to maybe spend some time having a look at this, because it's quite interesting really, because you can see that A and B can start at the beginning because they don't have any immediate predecessors. But you'll notice that both C and E have A as an immediate predecessor. So once A is finished, then C and E can start. You can also notice that G, for example, needs C and E to be finished before we can start task G. So let's have a look at G. We can see that G, this shows here that C has to be done before G can be done, but this little dotted line here is also indicating that E has to be connected, so that E has to be done before we can start G. This is what we call a dummy line. So it's a dotted imaginary activity task or line with a weight of 0 that's purely like a notational convenience. Dummy lines just exist to communicate like immediate precedence, for example. So because C is an edge and E is an edge, because edges represent activities when we're looking at this, I can't have G come out of C and E. That just doesn't make sense. I can't have it come out of two different vertices. So that's where dummy lines come in. By linking up there, we can see that, okay, so before I can start G, I know that C and E has to be done. And you can also see that this network is directed, and that communicates that like the tasks have to be done in a certain order, and we can see that flow throughout the network. And like I said, activities, they can be represented visually in networks, like what we have here. Oh, and I've already covered this as well. So the start of an activity depends on any predecessor activities being completed first. So immediate predecessors are activities that once completed guarantee that the current activity can be started. So think of immediate predecessors like prerequisites. You have to do year 10 before you can do 11. You have to do grade 3 before you can do grade 4. You have to crack the eggs before you can stir them in. Think of it like that. So edges are what represent the activity to be completed, and the weights represent the duration of the activity. So it might take 3 days for them to lay the concrete, for example. And then the vertices represent the start and the ends of the activities on either sides of the edges. And the dashed lines, which are the dummy lines that have a weight of 0, what I introduced earlier, they're required when two activities share some but not all immediate predecessors. and that accounts for shared immediate predecessors without needing multiple edges. So they're imaginary lines. They're a notational convenience to communicate that need. It's to communicate that this activity needs both of these as immediate predecessors without needing multiple edges. So we've covered that there. So the earliest start time an activity can commence is important because we want activities, most of the time we want to start activities as soon as possible. And not all activities can be started at the beginning due to predecessors, like what we've already talked about. And the earliest start time is found by forward scanning. So A and B, because they don't have any immediate predecessors, they can be started right at the beginning of the project. They can be started at time point 0. But we know that C and E can't be started until A has started, till A has finished. So if this, for example, represents hours, then C can't start until A has finished. So C can't start until 2 hours into the project. So the earliest time that C can start is whenever A can finish. So C can't start until we're 2 hours in. And we know that E is the same. E can't start till we finish A, so we can't start E until we're 2 hours into our project. Let's have a look at G. We can't start G until C and E are finished. So it'll take us 2 hours to finish A at the absolute quickest, and then it'll take us 10 hours to finish C. And then if we look at E, it'll take us 2 hours to finish A, 5 hours to finish E, and then we can come up here along the dummy line. So to get to this time point to start G, we can have A done in 2 hours, which means we can have A done by the time we're 2 hours into our project. We can have E done after 5 more hours, so we can have A and E done after 7 hours. So E is ready to go after 7 hours, but at 2 and then another 10 hours means A and C won't be done for 12 hours. So we actually can't start G for 12 hours because both C and E need to be finished for G to start. So that's kind of a theoretical introduction to how we use forward scanning to find the earliest start time. So for the sake of time, we're not going to go into this. I'll just continue to give you a bit of an overview of some of our most important information. But the basic idea of forward scanning is that we move through the vertex and we find the earliest start time of each activity using the process that I just modeled on the previous slide. And the earliest start time of each activity, we record that in the box on the left at the vertex at the start of the activity. So you can see that what I said here is true. A has an earliest start time of 0. It can start straight away because it has no immediate predecessors. C has an earliest start time of 2 because A takes 2 hours. So by moving along there, we can say that A has an earliest start time of 2. Then we can come down to E. E is going to take 5 hours. So this number here is going to be 7 because we know that it's going to take 7 hours at the absolute quickest and earliest to get to this point. But then if we come across up here, well, technically we could be here by 7 hours, but because it's going to take us 12 hours to get A and then C done, then we know that the earliest time we can start G is actually going to be after 12 hours into the project. So when we do forward scanning, we always choose the biggest number because we're always going to be held up by the task that takes the longest. And we are almost out of time for today, so I definitely encourage you to download the slides and go through each of them. I've put quite detailed instructions on each of them, so hopefully they'll make sense along the way, and I'm not going to have time to explain most of them, unfortunately. But we have gone through the earliest start time, and then latest finishing time is kind of the reverse, and we do that via backwards scanning. So the latest finishing time is what is the latest time I could finish this activity without holding up the project. And then we do that through backwards scanning, which you can see we've done in this graph here. And then by doing that, that can actually help us find out the critical path. And the critical path of an activity is what is the order or sequence of activities that, if delayed, will delay the entire project. What can we not hold up if we don't want to delay the whole project? And if you follow the path of numbers of boxes where the numbers are the same, that will actually help us find the critical path, which we can see in this here is along the top. So we can see that these activities are on the critical path. So if any of these activities are delayed, then we know it's going to delay the final finish time of the project. So that's just a really brief overview, but I definitely encourage you to go through these slides in a bit more detail in your own time, because I've put in all of the information here, for example, how to find the float times and what that means. So make sure you work through all of this yourself in your own time. So yes, please have a flick through the rest of the content. I also have a few exam hints and tips for preparation for the external that you can go through. So make sure you have a look at these ones as well, and as well as some tips for your external. But unfortunately, that is all we have time for today. So again, please feel free to download the slides and go through them. I've left lots of notes so you'll be able to work through them at your own pace and hopefully get a lot out of that as well. But yes, that is all we have for today. My name is Hannah. Thank you so much for joining us. I hope today's been really helpful and you've gotten a lot out of it. Thank you so much, and best of luck with the rest of year 12 and your externals. Thanks, guys.